All right, we're going to give a formal name to something that we've been doing a lot this semester. So if I would say to you, find a tangent line, what two things do you need to do that? Point and a slope, right. All right. The formal process, that is called linearization. Okay? It's the same thing as finding a tangent line. It's just a formal word for it, and so we're going to name it what it is. Okay, linearization. It's AKA finding a tangent line. Okay, if tangent lines need points and slopes, it's just that we're going to do something else with the tangent line now. It's like, oh, well, we learned that. Now we can do more with it. Oh, we learned a chain rule. Now we can actually do this. That's why we're revisiting this. Leibniz also has his own little tangent line thing. We'll talk about that. His were called differentials, and then we'll see how we use both of those to over and underestimate. So this comes in handy. It really revolutionized how people looked at math. I mean, calculus, it was just a rebirth. Math had stayed the same from the time of Archimedes all the way until Newton and Leibniz. There had been no major aha moments in math through that whole time. They just kind of kept passing on what they knew, but no major inroads or discoveries until we got to these two guys. Okay, and so it was just sort of that aha moment that we got there. It just improved the accuracy. Like the Greeks, they had the idea of pi. They had the idea of formulas like pi r squared and stuff, but they couldn't prove any of it. And it wasn't until Newton and Leibniz came up with calculus that we could actually prove the things that the geometers thought they knew. All right, so here we go. What Newton would do is he would say, okay, given a random function, I can get really, really close. Okay, well, here, let me start back up. What's the most important spot of that function right there? The zero. Okay, this is the most important point. Okay, of this function. Okay, and so they would go, I want to know where that is. Now, sometimes that works out easily. You can factor, and wow, it worked out great. Or you could do the quadratic formula and find it, and wow, that worked out great too. And they all could do that. But what if factoring only works if it factors, and the quadratic formula only works when?
Oh, the discriminator.
Well, if it's what kind of an equation?
Oh, a quadratic.
A quadratic. It's got to be a quadratic, okay? Otherwise, you got to learn the cubic formula, which is a really big mess. But what if it's a log? And what if it's an exponential? And it really only works. So we needed something else. All right, so what Newton did, assuming that point was an irrational point that was hard to find, Newton would find a different point. And he would say, okay, I'm going to find this one, and this is going to be an easier point for me to find. Okay, he would pick something that had nice round whole numbers. And what he would do is he'd calculate the tangent line right there, because he knew calculus now. So he could come up with the tangent line. And he'd sketch his tangent line. And his tangent line would come down and hit. And then they'd measure the gap of how far away they were. Bam, bummer. We're off by a little bit. That tangent line right here didn't hit exactly where I wanted it to do. So then they'd slide that point down a little bit. Okay, well, let me go straight up from there and let me find a new point. And I can find the tangent line on that. And let me find the tangent line. Boom. And then, rats. I'm close, but I'm not super close. And so then they would repeat it again, and they'd go straight up from that. And they'd find calculate the tangent line, and then they'd do it again until they got reasonably close to what that was doing. You know how on your calculator, when you do second trace and your calculator asks you for a left bound and a right bound? You know that process? This is exactly what your calculator is doing. You are giving your calculator a spot to start at. When you tell it the right bound, it starts here. And it also needs a left bound, and the left bound would start it down here. And then your calculator at lightning fast speeds is calculating tangent lines. Boom, 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 until the two tangent lines from both directions intersect at the same spot, and then it knows it's found its 0. And as long as it takes you to go left bound, right bound, guess, enter, and then it's done it. That's what it's doing that fast for you, okay? Newton was doing that by hand. He was calculating all of the approaches from the right, and he was calculating all the approaches from the left, and then eventually those two things would intersect each other, and then you would know that you would have your target, or the actual important point of the 0. That is what linearization is good for, what Newton used it for. I don't ever get to make you do that by hand. Okay, but I want you to appreciate what's going on, the smart people who are programming our calculators. Okay, and that happened in the 80s. Okay, because I went through high school 80s and college in the 90s, and I didn't have a graphing calculator. And when I got to teach here at Valley, I got my first graphing calculator, but I do this by hand. Okay, until we came up with it. It's a laborious process. All right. Yeah. You guys are, so then, but my problems were way easier. You guys get harder problems because you're holding a computer in your hand, okay? All right. So that's called the linearization process, okay? So you find your slope. You found your slope first. Find your point first. Your point will be a comma f of a. That's x and y. You find your slope, which would be f prime of a. And once you have your point and your slope together, your equation would become y minus f of a equals f prime of a, that's the slope, times x minus a. This is the point slope equation. And most commonly, you'll see y by itself. Okay, so what would you do to get y alone? Add. Okay, so you'll see the slope in the front, and then you'll see added f of a at the end. Okay, this is just the point slope equation. It's what we've done dozens of times already. All right, the other thing that tangent lines do is measure that gap distance here. Okay, see the gap distance like this? Okay, on either side I can go and measure that gap distance. All right, that gap distance between the curve and the tangent line is affected by the concavity of the curve. Hey, what kind of concavity does this picture happen to have? Concave up. And because it's concave up, the tangent line will always be underneath it. It'll always skim off on the bottom part. So this is a concave up. Whoops, I can't spell. And the tangent line will always be below. And instead of using words like below, we say under approximate. The tangent line will under approximate or underestimate because it was concave up. The opposite is true. If you're dealing with a curve that's concave down, then the tangent line will always overestimate and skim off the top. Let me show you a picture of that. I've got that 2 slides from here. Okay, so let's just go down slide 7. The concavity of f of x will determine whether or not the L of x, okay, L of x is what they used for linearization. So the concavity determines whether or not the linearization will be too big or too small. In other words, if your guess will be too high or too low. It's always based on the concavity. So this is another reason we check the second concavity, a second derivative. We check the second derivative to tell whether something is a max or a min. We also check the second derivative to know if our linearization is going to be always bounded underneath, always be below, or whether it would be always above. Okay, here's a picture. Okay, so kind of shade in like a little bit of the gaps here. All right, that is a concave down section. And so the red tangent line is always above it, always higher than it, always overestimating. So this is an overestimate or an over approximate because the curve is concave down. But then at that point of inflection, it changes. And now you have that gap or curve here. Okay, that gap growing this way. And now we have an underestimate on my linearization because I have a curve that's concave up. So this becomes part of your justification, part of your answers. They'll say, you know, find your answer, and then they'll say, will your answer be an underestimate or an overestimate of the actual answer? And then you'll reference the second derivative to know if it's going to be an over or under estimate of the approximation. So we're going to practice that. Okay. Given a quartic function, find f of negative 0.9 without a calculator. Okay? Without using your calculator. All right. So Newton would say, forget that. I don't want negative 0.9. That's too hard. Newton would pick a closer number. Okay? What would he pick?
-1.
For sure. Okay? And then Newton would say, okay, I'm going to find a tangent line at -1 instead. All right? So you're going to switch gears and you're going to go with something that's easier. So that's step one. Choose an easier starting value. And we're going to pick x equals -1. We're going to find our point, and we're going to find our slope. All right, what would the point be? Again, no calculator, but it's just -1. You can plug in -1, right? What do we get? 2 minus 4 minus 3. So how much? -5, okay? And then slope. What can we have there? All right, so slope would be 8x cubed plus 4. And we're putting in -1 into that. So 8 times -1 cubed plus 4. So what will that turn out to be?
-4.
-8 plus 4 is -4. Okay, so we have a point and a slope. So my linearization, or my tangent line, would be y plus 5 equals -4 times x plus 1. Okay, now plug 0.9 into that. Plug x equals -0.9 into the linearization instead, because that's easier. Why is the linearization easier? What doesn't it have that the first equation did? Doesn't have a square, doesn't have a power, it's just a linear number. So I'm going to plug in -0.9, so I'm going to get y plus 5. Actually, I'm going to move the plus 5 to the other side. Is that okay? If I do that, I'm going to put my plus 5 over here. All right, so y equals -4 times -0.9 plus 1. All right, now that's easy math. It should be. What's -0.9 plus 1? I believe it should be positive 0.1 plus 5. And that's easy math. Yeah.
Is it -5? Because it was +5.
Oh, yeah. I moved it and I forgot to change the sign. Thanks, Chloe. Okay. All right, so what's 4? -4 times 0.1. -0.4 minus 5. What do we get? -5.4. Okay, now I dare you. Get out your calculator and now plug in -0.9 to the original equation and tell me how close Newton was.
Plug in the linearization of the original function.
No, into the original, do it with a calculator, okay? So the first, we did find f of 0.9 without a calculator. Now I'm telling you, you can use a calculator. What is it? So negative 0.2 times negative 0.9 to the fourth plus 4 times negative 0.9 minus 5.
Negative 5.2878.
Okay. So compared to the actual negative 5 point, say it again.
2878.
All right, so we'll say 5.3. All right, so Newton got 5.4 and the actual answer was 5.3. Okay, not too bad, not too shabby for Newton. Yes, sir. Yeah, Ethan?
No, I think I
Plugged the wrong thing in? Okay. Yeah.
So we're just finding the answer close to the real.
We're estimating as if, yeah, back in the, like when Newton couldn't do it with a calculator, he would say, I'm going to do it without a calculator, and this is his method of estimating. I mean, he could have done the math without a calculator by taking negative 0.9 and doing it to the fourth power and multiplying and multiplying and multiplying, but his argument was that it's faster. Okay, we already did that. Okay, we already did that. All right, will this have overestimated or underestimated the actual value? We already know what kind of estimate it was, right? He said negative 5 point what? 4, and what did it actually turn out to be? Negative 5.3, so it was an overestimate. Okay, how would you have known it was going to be an overestimate?
Concavity.
Let's check the concavity. Okay.
Wait, it'd be an under.
Oh, now we're talking negative numbers, other way around, right? Sorry, it was negative. Okay, so it's going to be it was an underestimate. So we had 8x cubed plus 4, and then the second derivative is 24x squared. So no matter what you plug into that second derivative, what will always happen to it? Yeah, because a square is always going to be positive. So this means it has positive concavity. And a positive concavity always means underestimation by a little bit. All right, and we already checked it with our calculators. Our calculators said negative, turned out to be negative 5.3. And we already answered that. Okay, I was going to have you do it with cosine also. That's the same idea. What would you pick that would be close to pi halves? Pi is really far away from pi halves. 3 pi fourths is too far away. Because you're doing it without a calculator. Pi halves? Only if you have a radian mode, then you can type in what that is. We're doing 1.57. Oh, sorry, 1.75, right? So pi halves would be what you, sorry, I asked the question in backwards. If we're trying to find 175, we'd pick pi halves because pi halves is the nicest closer number. Sorry, I asked my question in reverse. You're right. All right, so we can apply the same idea to evaluating trig functions. All right, so let's think about how Newton would approach this, right? So let's think about cosine of pi halves. All right, so even Newton, everybody knows that that's equal to 0. But what is the cosine of 1.75? All right, that's the question. Can we figure that out without using a calculator, right? Okay, so Newton would say, okay, well, I'm going to go with the one I know. I know cosine of pi halves. So the point that he'd work with would be pi halves and 0. The slope he would work with would be the derivative, the negative sign of pi halves, which works out to be negative 1. So then his line would be y minus 0, which we don't really need. So let's get rid of that. And then equals the slope of negative 1 times x minus pi halves. All right, and he'd say, okay, I'm going to use that instead, and I'll find, instead of plugging in 1.75 into cosine, like this, okay, I'm plugging 1.75, I'm going to plug 1.75 into that equation right there. So y would be equal to negative 1 times 1.75 minus pi halves. So that would be 1.75 minus 1.57. That's approximately what pi halves is. So the subtraction on that. And we get negative 0.18. If we compare that actually with our calculator in radian mode to the cosine of 1.75, we get negative 0.178. So only off by, 22 thousandths of a decimal point. So pretty good for little old Newton. All right, so how would Leibniz approach that? So let's just remember the difference in their notation. If Newton used f of x and Leibniz used y, and then Newton used f prime, and then remember that Leibniz used dy dx to denote his derivative. So what Leibniz called those pieces, he said dx and dy by themselves are called differentials. And two differentials together make a derivative. And so he said, well, I can move those around. I can cross multiply with them. I can, think of them as independent pieces, mostly using them for cross multiplication. So what that would look like mathematically if you had a derivative, say it turned out to be equal to 5x, let's say that. Okay, you could cross multiply here, and those pieces, the dy dx's, could be separated from each other. So dy would be equal to 5x times dx, and those pieces you could just manipulate them. All right, what in terms of what they mean, okay, dy dx, remember, means slope. But dy by itself means how much y changed individually, separately from x. And then the dx would be how much the x changed individually, again, from y. So the slope measures the change together. It's a ratio, rise over run. So it's the slope of the overall change. But you can separate and look at them in two individual ways. It's a lot like vectors, okay? And you know how in vectors we separated the x stuff from the y stuff, so you could look at, well, if I change x, then what will y do? It's so much like that. Parametrics do the same thing, where you can look at an x variable separate from a y variable and just tweak one or the other and then see what kind of an impact it had on the other. So here's how this would look. Let's think about a circle. So geometrically, we're thinking about a circle's area. So A equals pi r squared. And then we want to estimate how much the area itself would change. So we look at the overall change. That would be dA respected to the other variable. So the other variable in this case would be r. So it would be dA dr equals. And then when we take the derivative, since pi is a constant, the 2 is going to go out to the front. And so we would have 2 pi r. We can cross multiply in this situation, put that over a 1, do a little fancy cross multiplying, and we get dA is equal to 2 pi r times dr. So how much A will change, the change in A, is equal to 2 pi r times the change in r. All right, and so the question is, use dA, which we have now, to estimate the increase in the circle's area if we go from 5 to 5.1. And so here's what this is going to look like. It'll be 2 pi. The radius is equal to 5, so 2 pi times 5. And then dr is how much the radius is changing. And so it's an increase of 0.1. So we multiply that by 0.1. It's not the whole 5.1, it's just the increase or just the change. So that works out to be 2 times 5 is 10 times pi. The fraction for 0.1 is 1/10. And so that simplifies to just be pi. So that means overall that if you change the radius of a circle by just 1/10, that the area will have a resulting change of pi, or 3.14. So let's kind of put that into context, right? R changes by 0.1 meters, but the area is going to change by 3.14 meters squared, right? I mean, you change the radius just a little bit. Everybody thinks, oh, 0.1, it doesn't hardly matter. But you end up changing it by over 3 units of a square meter. That's a big resulting change as those two things are connected to each other. Let's try another one. All right, so we're given an equation. We're given what x is, and then we're given how much we're going to change x by. And we're going to see how that impacts the equation. So we look at dy dx, which turns out to be 5x to the 4th plus 2. Okay, put a little 1 under that, do a little cross multiplying. So the dx ends up on this end when I cross multiply. Let me just clean that up. Okay, so there we go. So 5x to the 4th plus 2 in quantity, and then multiplied by dx. So what would dy turn out to be? So dy would be, x is currently 1, so that's 5 times 1 to the 4th plus 2. And then dx is 0.01. So that's 7 times the fraction 1/100th, or 7/100th. So in other words, what are how would you interpret that? So dx means change x by 0.01, and dy would be the result, the resulting change in y will be 7 times bigger, 0.07. Okay, if you change your x by a little bit, it's going to change the y by a lot more. Will this situation be an over or underestimation? Well, again, we just have to check the second derivative. We need to know about the concavity to know about whether it'll be an over or underestimate. So my second derivative is going to be 20x to the 3rd. And in this case, 20 times 1, so that's 20. That means this equation is, or this function is concave up because it has positive value. Concave up always means an underestimate in your differentials. Okay, sometimes it helps me to picture it. Concave up, and my tangent line will always underestimate. So this would be an under approximation of the actual value. So what that means is if we're predicting that a change of x by 0.01, so a lot of engineers will do this. If I change the size of this hole by 0.1, how will that impact, what comes next? So we're saying, all right, if you change this variable by 0.01, it will have a resulting change, a predicted change of a factor of 7 larger, so 0.07 in y, and we think that's going to be an underestimate of the change, so it's actually probably going to impact it even more, okay, even higher than what it originally was. So that's what you use the second derivative for. All right, I look forward to starting our very last lesson of the whole semester with you tomorrow, and we'll take a couple days to get through that. All right, so see you on Tuesday.